The topic of this lecture is text classification. My name is Johan Hagelbeck and I'm a senior lecturer at Linnaeus University. So text classification or document classification, it's a very common machine learning problem where we classify a document based on its text contents or a subset of it, the text content such as the abstract of an article. And we use the text contents as input to a machine learning algorithm and outputs which category the document most likely belongs to. And the probably earliest and most common application is spam detection. We want to classify if an email is spam or not based on the text contents of the email. And spam filtering can also be used for entries and comments on blogs and social media, etc. And the very early systems for spam detection were based on rules. And programmers manually designed a set of rules that could detect spam. Rules could, for example, detect overuse of capital letters, words related to pharmaceutical products or Rolex watches, very common early spam, overuse of eye-catching colors, etc. The biggest problem with this approach was that spammers learned about the rules and created spam that could circumvent the rules. And it was a constant battle between the spammers and the rule programmers. Another problem is that what is spam or not depends on the user. Advertising or drags could be normal for a pharmacist, but unwanted for a programmer. Therefore, we needed spam filters that can learn from what the user wants. Modern spam filters also take into consideration the sender of an email, but that is out of scope for us. We're just interested in the learning problem. And for that we use the text contents of an email or a comment or anything. There are several algorithms that can be used for text classification. Artificial neural networks, support vector machines, k-nearest neighbor algorithms, decision trees, or approaches based on natural language processing, etc. But we today will focus on a simple but yet very powerful and very common algorithm called naive Bayes. First, we need to learn about what we call Bayes' theorem. It describes the probability of an event based on prior knowledge of conditions that might be related to the event. The Bayes' theorem is stated using the following formula. PA given B equals to PB given A multiplied by P of A divided by P of B. And where with P parenthesis A vertical sign B shall be interpreted as probability that the event A occurs given B. And is best explained using an example. We are interested in an answer to, is stiff neck a good sign of being a good FIFA player, the FIFA video game? To answer this using Bayes' theorem, we need to know the prior probabilities. And it could be that 50% of the good FIFA players have a stiff neck. So the probability of having a stiff neck being a good player is 0.5. 1 in 50,000 players is good at FIFA, so the probability of being good is 1 in 50,000. And 1 in 20 players, both good and bad players, suffer from a stiff neck. So the probability of having a stiff neck is 1 in 20. And we can now use these prior probabilities. Probability of stiff given good is 0.5. Probability of good is 1 in 50,000. And probability of having a stiff neck is 1 in 20. And we can use these to calculate the probability of being a good FIFA player if you have a stiff neck. So we just take our formula and put in what we're interested in. We're interested in probability of being a good player given a stiff neck, and that's calculated as the probability of having a stiff neck being a good player multiplied by the probability of being a good player divided by the probability of having a stiff neck. And we just put in our numbers and we do some calculation, and we see that the probability for a player having a stiff neck and also being good at FIFA is just 0.0002, so very low probability. So we can use these given prior probabilities and put them into Bayes' theorem, and we can say that it's a probability of 0.002, a very low probability that the player is actually good at FIFA if he has a stiff neck. So only having a stiff neck is not a very good indication that the player is good at FIFA. Or if we turn it around, 1 in 5,000 players with stiff neck is good at FIFA. The Bayes' theorem only takes one attribute in consideration, here the stiff neck, when calculating the probability of belonging to a specific category, if we are a good or bad FIFA player in this case. And most real-world applications have more than one attribute. We can have stiff neck, that's good, one sign. We can have a good gamepad, we can have a large TV screen, and all of them in some way contributes to our guess if a player is good or bad at FIFA. And we need a way of combining these several inputs to get the probability of belonging to a specific category. And this is handled by the naive Bayes classifier. The classifier is called naive because it assumes that the attributes are independent of each other. It means that the probability of one attribute belonging to a specific category is completely unrelated to the probability of other attributes belonging to that category. So there are no relation between attributes. And this is actually a false assumption. For example, the word money is a better spam indicator if in combination with casino than with programming. So the independence between attributes means that the actual probability calculated by the naive Bayes classifier is inaccurate. It's not a true probability. So you cannot say that the resulting probability is the actual or true probability that the document belongs to a category. But the good thing is that we can compare the results of a document belonging to different categories and see which has the highest probability. And this actually works surprisingly well for real-world document or text classification problems. So the naive Bayes classification works like this. Calculate the frequencies of each attribute belonging to each category, and for each category multiply the conditional probability of each attribute into a product, multiply the product with the category probability, and classify the document as belonging to the category with the highest probability. So actually quite a few steps, can be a bit difficult to understand, so we take an example that's usually easier to understand what we mean. So we have a bit larger data set, but still a simple data set. We have the quality of our gamepad, if it's great, average or junk. We have the stiff neck, yes or no, and we want to use these two attributes to decide on a category player skill if a player is good or bad at FIFA. So we first take the data set and we put it into a frequency table. So gamepad, if we look at the data sets, we have one example where we have gamepad great and player skill good. We have one example where we have gamepad great and player skill bad. We have two examples of average gamepad and good FIFA player, and three examples of average gamepad and bad FIFA player. The second stiff neck, we have three examples of stiff neck, yes, and being a good FIFA player, and only one examples of having a stiff neck and being a bad FIFA player. If we don't have a stiff neck, we have one example of being a good FIFA player and four examples of being a bad FIFA player. And the player skill, we see that we have four examples of good and five examples of bad player skill. So that's the frequency table that covers the complete dataset. And we continue using the frequency table to fill in the prior probabilities. So the probability of having a great gamepad given good FIFA skill is 1 in 4, because we have one example and that is great and good, and 4 examples of good. Same goes with great gamepad and bad player skill. We have one example of being a great gamepad and bad FIFA player, and we have in total 5 examples of bad player skill. The average gamepad, we have 2 examples of being good, so 2 divided by 4 is probability, and we have 3 examples of being bad and average gamepad, and we have a total 5 bad examples, so 3 divided by 5. And we just continue filling in all the prior probabilities in this table. So I have a table of frequencies and a table of prior probabilities. And that table is actually all we need for classification. Now we can answer questions like, a player has an average gamepad and a stiff neck, is he a good or bad player? Or a player has a great gamepad and not a stiff neck, is he a good or bad player? And we have two possible categories, the player being good or bad at playing FIFA. So let's calculate the probabilities of the above mentioned player belonging to the 2 categories. So we want to classify the example of a player having an average gamepad and a stiff neck. The probability that the player belongs to the good categories is probability of being good multiplied the probability of having an average gamepad given good player skill, and the probability of having a stiff neck given good player skill. And we just look up all these numbers in our table, and we see that it's 4 divided by 9 multiplied by 2 divided by 4 multiplied by 3 divided by 4. And it results in a probability of 0.1667. And we do the same thing to calculate the probability that the player belongs to the bad category. And it's calculated as the probability of being bad multiplied the probability of having an average gamepad, because that's in the example we want to classify, given bad player skill multiplied by probability of having a stiff neck given bad player skill. And we just look up all these numbers in our table and we see that it results in a probability of 0.0667. And the results here show us that it's a higher probability that this player that has an average gamepad and a stiff neck is good than the player being bad, so we classify that this player is good as FIFA. If we take another example, we have a great gamepad but no stiff neck. We put in the values in the formula for the player being in the good category. The probability of good divided by probability of having a great gamepad given a good player skill multiplied by probability of not having a stiff neck given good player skill. We look up these numbers and we see that the result is 0.0278. The probability that the player belongs to the bad category is equally the probability of being bad multiplied the probability of having a great gamepad given bad player skill multiplied the probability of not having a stiff neck given bad player skill. We look up numbers in the table and we calculate and see the result is 0.0889. And we can see here that it's a higher probability for bad than good, so we classify this example as the player belonging to the bad skill category. In many applications, it's better to return a don't know than a misclassified document or example. In spam filtering, it's more important to avoid having legitimate email classified as spam than to catch every single spam message. And this can be solved by using a threshold. If we, for example, use a threshold of 3, it means that the probability for the highest category must be at least 3 times higher than the probability of the other category, otherwise the classifier is unsure. In our example, we use the threshold of 1, meaning that we always classify as the highest category, regardless of a difference in probabilities. So we can take the same example, the two examples we have here. Previously, the probability for the first example being in a good category is 0.1667, and the probability for it being in the bad category is 0.0667. And the ratio is around 2.5. And if we use a threshold of 1, we classify it as good because we only look at which of these probabilities are the highest. If we use a threshold of 3, it means that the threshold of the highest category must be, the probability of the highest category must be at least 3 times higher than the probability for the other category, and the ratio here is only around 2.5, so we classify this example as don't know. In the second example, we have a probability of being a good player, 0.0278, probability of being a bad player, 0.0889, and we see that the ratio here is above 3, so in both cases, if we use a threshold of 1 and 3, we classify this example as being a bad FIFA player. The approach described here is what we call a multinomial naive Bayes. There are a number of other variants of naive Bayes, mainly Gaussian and Bernoulli. In Bernoulli, we don't count the actual frequency of an attribute in a category. Instead, we use 1 if the attribute appears in any example or document belonging to the category, and 0 otherwise. In Gaussian, we assume that the attributes are numeric and follow a normal distribution. In the examples we have seen so far, we have had 2 attributes. We have a gamepad that could be great, average, or junk, and we have a stiff neck, which could be either yes or no. In document classification, we have to classify texts of different length. To do this, we first have to convert the text contents of each document to a bag of words. Then we have to count the frequency and calculate the probability that each word belongs to each category. So let's look at a simple example of spam filtering. We have 5 short sentences: buy cheap Rolex, that is a spam. You want Viagra, that's also spam. Can you buy milk? Not spam. I want candy tonight, not spam. Want to go to the gym? Not spam. So a very small and simple data set. To create our bag of words, we need to find the unique words here, all special characters removed, and we change to lowercase for all words, and we see that the bag of words will be buy cheap Rolex, you want Viagra, can milk, candy tonight, and gym. So in some cases you appears several times, tonight also appears several times, buy as well. And the next step is to create a frequency matrix for all the unique words, similarly to the previous FIFA example. So buy appears once in both a spam email and once in not spam email. Cheap appears twice in spam emails and 0 times in not spam. Rolex appears once in spam and 0 in not spam. And we continue just filling in the table and also calculate the probability of belonging to different categories. So we have 2 examples in the yes category and 3 examples in the no category. And the next step, similarly to what we did before, is to fill in the probabilities, and it's just take the numbers. For buy, probability of buy given yes or no is 1 divided by 2. We have 2 examples belonging to yes, and 1 divided by 3. We have 3 examples belonging to no. The word cheap, 2 times belonging to yes, so 2 divided by 2. 0 times belonging to no, so 0 divided by 3. We have 3 bad examples, and we just fill in the table. And once we have filled the table, we can classify new examples. So in this example, we want to classify if buy cheap candy is spam or not. As in the previous example, we calculate the probability for being spam or not being a spam. So in this case, the probability of being a spam is probability yes, multiplied probability of the word buy given yes, multiplied by probability of cheap given yes, multiplied by probability candy given yes. And if we fill in the numbers here, we see that the result will always be 0 because candy is never appeared in examples belonging to the yes category in spam emails. And that's a problem. If a word has never showed up in a category, we multiply with a 0 and the result will always be 0 regardless of the probability for the other words. And we need to solve this somehow, and one way of doing is to apply what's called a Laplace correction. And in Laplace correction, we always add some constant value to each probability to avoid 0 probabilities. A common way is to use 1/3 as Laplace correction to the probability for being spam. Looks in this case like probability of yes multiplied probability of buy given yes, probability of cheap given yes, probability of candy given yes. 2/5, we don't apply any constant to the first class category because that we always have some examples in both our categories or all our categories. The second is buy appeared 1, and we have 2 examples of yes, so 1 divided by 2 plus the constant 1/3. Second, 2 divided by 2 for cheap given yes plus the constant 1/3. And the third example, candy given yes, that's 0 divided by 2. Candy never appeared in spam emails plus our constant 1/3. And now we can actually calculate the probability. We don't have a problem of always ending up in 0 probability, and the result is 2.9. We can do the same for this not being spam. That's probability of no, multiply probability of the word buy given no, multiply the probability of word cheap given no, multiply the probability of word candy given no. And we just take the numbers. 3 out of 5 example is in the no category. Buy given no, that's 1 divided by 3 plus the constant. Cheap given no is 0 divided by 3 plus the constant, and candy given no is 1 divided by 3 plus the constant. And that ends up in 0.089. So in this case, it's pretty clear that this message will be classified as the yes category, classified as spam. So the text buy cheap candy was clearly classified as spam, but is this correct? The word that is most prominent in the result is cheap, which exists in 2 of 2 spam and 0 of 3 legitimate messages. And if cheap is not a good indicator for spam, we need more training data where cheap appears in both spam and legitimate messages categories. And we need quite large amounts of data for text classification to be accurate. We can do text classification in the Weka machine learning collection. So as mentioned in the previous lecture, Weka is a collection of machine learning algorithms, and it has a GUI tool and an API library. And Weka has been around for several years and has been used in numerous projects. And you have a link here to download it. It's developed at the University in New Zealand. And we will now take a look at how we can use Weka to classify the Wikipedia dataset, which is a document classification problem where we have 2 categories. We have games and programming. And this subset of a total Wikipedia dataset that are generated consists of 35 articles about programming and 35 articles about video games, and that's quite enough for these classification tasks. All tags and code has been removed, and the text has been converted to a bag of words, and the data is stored in an ARFF file, and that's short for attribute relation file format, and that's the dataset format Weka uses. Weka can also use CSV files, which is more common format. The first part in the ARF file defines a name for the classification task and each attribute with their respective type. So the classification task, the relation, is called Wikipedia, and the first attribute we have is called text, and it's a type string. The second attribute is called article type, and it has one of two possible categories: games and programming. This is followed by the actual data. So we have the actual text within exclamation marks, and we have a category programming. Second example belongs to category games, and so on. The attribute types that Weka supports is strings, that's text; nominal, that's a fixed set of values. In this case, we have the article type is nominal, and then we add the possible categories, games and programming. Or it can be numeric. Attribute temperature is numeric in the weather dataset. Each attribute is separated with a comma, and in our case we only have one attribute, the text, and a category, and the text must be within these single quote marks. Weka is very strict with which single quote character you use, so make sure that you use the correct one, otherwise we get an error when you try to load the dataset. And each row in the file is called an instance or example in Weka. So, to run it in Weka, we double-click the Weka YAR file, and it should open the Weka application, and it starts with a window where we select what we want to do with Weka. And the most simple way is to use the Explorer interface, so we click on that one. And the following window is shown. We click the Open File button, and we select the Wikipedia_70.arff data file, and you can download it at the course web page. And once it's been loaded, we see that the data set have two categories, two attributes, text and article type. And now we need to convert the text attribute to a bag of words. So we click the filter, the choose button in the filter, and we select the filters, unsupervised and attributes, and the string to word vector filter. And now we have loaded the string to word vector, and now we click the apply button. And when we click apply, we see that we have all the bag of words as all the possible words in this bag of words as attributes. And we also see that some special characters are left in the file. We have an and, plus, etc. So now the dataset has been filtered and to a bag of words, and it's ready to be classified. So we click the Classify tab, and it brings up this window. We have the start, the CR, the baseline classifier. We see that we need to select which of all the attributes that are our class attributes. So we click this drop down box and move to the top and select the article type as the class attribute. And we select a new classifier, so we put the choose button and we select the Bayes and the naive Bayes multinomial classifier. And once it's been selected, we click the start button. And when Weka is ready, we see that 97.1429% of the 70 examples is correctly classified. So 68 out of 70 examples are correctly classified. So that's a very good result. And the complete result output from Weka is here. We can see quite a lot of information. The line correctly classified instances, tells us the accuracy, 68 out of 70 articles were correctly classified. And the confusion matrix, as mentioned in the previous lecture, is often very interesting. In this case, we see that the game documents are slightly misclassified. 33 is correctly classified, but 2 is incorrectly classified as programming, while all the programming documents were correctly classified. We also have the other scores we talked about. We have a true positive rate, false positive rate, F measure, etc. So Wiki outputs quite a lot of metrics for us, and we can choose which metrics we want to use when we present our results. So, at the end of this lecture, we will look at a more realistic case. This is a student project I had together with Visma in Växjö. And the task was to detect or distinct between receipts and invoices. Visma has an accounting system, and a user in this system uploads a picture of a receipt or invoice, and the user must then select if the picture represents a receipt or an invoice in a drop-down menu, and it's quite easy to misclick or forget this step. So the project wanted to automatize this with machine learning. So to do this, the first step was to actually use an optical character recognition system, because we have an image of a receipt or an invoice, and we need to find the words, the bag of words in these images. So as OCR can use, for example, Google Vision or FineReader. In this case, the students used FineReader, and we get a bag of words out of these images. So the images are fed through an OCR system. We get a bag of words. The bag of words are fed to a naive Bayes classifier, and the output of a classifier is if this image represents a receipt or an invoice, and we can use it to automatically classify these images in the Visma accounting system. And we had a small test set, because it was only a pre-study if this was actually possible to do in the system. So the dataset consists of 37 receipts and 38 invoices, in total 75 images. And in this case, we were able to correctly classify 97.3% of the images. And it was enough for Visma to actually use it in production, but as far as I know, the project hasn't been continued yet to being any, it hasn't been used in the system yet. So that was all for this lecture about text classification. Thanks.